In this video, we're going to look at how we can use a heap to sort an array. So at a high level, the steps are basically this. Construct a max heap, and then 2, repeatedly remove the max element, reheapifying after the removal. That is, we take the max element, we now have a heap that represents an array of one less element, and we need to reheapify to fix the array. And we'll go into more details about this later. Now, if you don't really understand how heaps work, I have another video that discusses that, and I'll link to it in the description below. But we'll start with the first thing, because it turns out this is where most of the cost will come from. There's different ways to construct a max heap. So let's look at a couple ways. So let's say that we have this array, 1, 2, 3, 4, 5, and we just want to build a max heap from it. We're not sorting yet, because it turns out this actually would already be sorted, right? So one way to do it would be to use insertions. Okay, and we're not counting, it's just insertions, right? So the way that works, and this is what I demonstrate in my other video, and it's a fairly common way to teach how to build a heap, is you start with the first element. And remember what we're doing here when we talk about building a heap, we're still storing the values in an array. It's just that we're thinking about relationships between them that satisfy certain properties. And in the case of a max heap, we have that the value of a parent node is greater than or equal to the values of its child nodes. So we start with 1 and we check the heap property. Since there's no child nodes, this satisfies the max heap property. Then what we're going to do, we're going to add 2. But now when we check the max heap property, we see it's violated because 1 is not greater than or equal to 2. So we need to heapify, and that means swapping these values. And in the array, the 1 and 2 would get swapped here. And now what do? We're going to add 3 to the next location, and we check the heap property. Well, 2 is not greater than or equal to 3, so we need to swap, and that would give us this. And of course in the array, what we really have would be 3, 1, 2, and of course the 4 and 5 are still there. Now we want to add the 4. Check the max heap property, it's violated here, so we swap the 4 and the 1. So have the 3 and 2, and now we check the heap property with the 3 and the 4, that's violated. So we fix it and we have 4, 3, 1, 2. And now we want to add the 5, it goes right here, check the heap property, it's violated. So we swap 5 and 3. Check the 5 and 4. The heap property is violated, so we swap the 5 and the 4. And this is our final heap. And that leads to the array 5, 4, 2. 4, 2, 1, 3. Right? So why didn't we need to keep moving the 4 down? Well, 4 was already higher than everything below it here other than the 5. Therefore, moving it down doesn't change that fact. So that's one way to do it. There's another approach that can be called bottom up. And in that approach, what we do is we go ahead and construct a binary tree from our values. So we have 1, 2, 3, 4, and 5. Now this is a binary tree, but it's not necessarily a heap. It could be, depending on the order. If these had been reverse order, 5, 4, 3, 2, 1, this would already be a heap. But that's not what we have. So what do? What we look for is the last parent node. And what would that be here? Well, 3 is not a parent. 4 and 5 aren't parents. 2 is the last parent node. And in terms of indices, if we think of this having index 1, 2, 3, 4, and 5, just as happens to be also the same values we have, but nonetheless, this would be index 1, 2, 3, 4, and 5. If we use this over here, we say we take the 2 for the index and divide it by 2 and find the floor of that, or excuse me, nodes. We have 5 nodes. We take 5 divided by 2, take the floor of that. 5 divided by 2 would be 2.5. The floor of that was 2. That would be the starting point. And then after that, we would use node 1 and so forth. So we look at this and we want to fix this if necessary. We compare 2 to 4 and 5 and see that 5 is the largest. So we still have 1. Now we have 5 here, 2, and the 4 and the 3 stay where they're at. If this had been part of a larger chain, we would need to keep moving the 2 down, but it's not, so 2 is as far down as it can go. So now what we do is we move to the next parent node, which is where the 1 is at, and compare it to its 2 child elements. What's the largest of the 3? Well, that's also the 5 here. So here we have 5 and 1, 3, 4, and 2. And because 1 swapped down, we need to check this node to see if it still satisfies the max heap property. It doesn't, so we figure out which of these is the smallest, or excuse me, the largest, and that would be the 4. So we have 5, 4, 1, 2, and 3 over here. So 5, 4, 3, 1, 2, and now we have a max heap, and the array here is 5, 4, 3, 1, 2. Okay, so it's not sorted. Our goal here was not to sort, it was simply to build the max heap. And we see the values are a little different from the 2 approaches. That's just how it worked out. But really, it took less work for this. So let's actually put cost to the 2 things and see how they work in general. Okay? But this right here now is a heap. So let's look at the cost for the insertions. Let's think about what we did. In this particular case, we saw the worst case, and that is when we added a 2, it had to be swapped up to become the new root. When we added 3, it needed to work its way up to be the new root. When we added 4, it had to work its way up 2 levels to become the new root over here. When we had 5, we had to work its way up, or we added 5 here, it had to work its way up 2 levels to become the new root. Had we added 6, it would have been attached here. It would have had to work up 2 levels to become the new root, 7, 8, 9. Every node in the worst case has to work its way all the way from the bottom where it was added up to the top. And let's see what the costs for that are. So here I've already worked them out, trying to make sure I hopefully don't make any mistakes. But if we look at this particular binary tree where I filled out every level to make it easier to follow, this is level 0, level 1, level 2, level 3, and so forth. If we think about forming a tree consisting of only one node, what is the height of that tree? Well, the height is 0. And then if we think about this tree, it has a height of 1, which happens to also be the level. That tree has a height of 2 because there's one level here, another level here, that's 2. One level, one level, one level, that's a height of 3, which is level. So ultimately, as we work our way down, counting these branches as we work down, the height of that tree will be the floor of log base 2 of n, where it's a number of elements. If we were to look at this part here where we had 7 elements, log base 2 of 7 would be greater than 2, but less than 3. We take the floor of that, which would just give us 2. That would give us the 2 right here. But we can use the level to determine how many nodes are at that level. So there's 1, 2, 4, 8, 16, and so forth. And we need to know that because if we're looking at the total cost in the worst case, we have the cost of swapping up for each node at that level. So there's no cost for moving up for the root. There's a cost of 1 for each of these 2 nodes. There's a cost of 2 for each of these 4 nodes, a cost of 3 for each of these 8 nodes, and so forth. So we have that summation, which I've written out here. And notice for the first one, I have 0 times 2 to the first, which will still be 0. So technically I can represent the summation using this formula here. And the reason I'm interested in that is because it turns out there's a closed form solution for this right here. Basically, the closed form solution says if you go from I equals 1 to k of I times 2 to the ith power, that's equal to k minus 1 times 2 to the k plus 1 power plus 2. And here our k is the floor of log of n. Okay. So now if I take this right here and multiply it out, I get this right here. And we need to figure out what to do with that. Well, if n had been a power of 2, such as, for example, if it had been 8, I would have log base 2 of 8 would be 3, and 2 to the third power would just be 8, which would be n. But we don't have that right here because we could have had log base 2 of 9 or 10 or something else that's not a power of 2. But this right here is bounded above by n. That is, if I had log base 2 of 8, I would get 3. But log base 2 of 9 would also be 3 if we have the floor. So we have that n is greater than or equal to 2 log base n where we use the floor. So I can use this less than or equal to bound this expression. And out of these 3 parts, the dominant term is n log n. So this is big O of n log n in the worst case. If this was already in order, which is best case, we don't have to do anything, so it has a constant cost, just evaluation that it's already the way it needs to be. Now the other approach was this, where we had started with the entire binary tree, and even though we started at a parent and checking that parent, basically what happened is we're looking at how things move down, because ultimately the 1 had to move all the way to the bottom, like we saw here. So 1 had to go down 2 levels here. 2 could have moved down 1 level. If we'd had more nodes, say if we'd had this or this, 1 could have moved down 1, 2, 3 levels. 2 could have moved down 2 levels. 4 could have moved down 1 level. So now if we look at the cost, what we get is this, is that if we have the summation of the height minus the current level, like here level is 0, the most that the root will have to move down would be 2 in this particular case, right? The height of this tree is 2, so 2 minus 0, because the level is equal to 0 here, gives me 2 times the number of nodes at that level. There's only 1 node here. Each of these 2 nodes can move down 1, which is taken care of here. Each of these 4 nodes moves down 0. Okay? Now on the surface, you may look at the process and say, well, isn't it basically the same as what we had before? And it is true that this process here, in the worst case, is bounded above by n log n. But it turns out that we actually can come up with a tighter bound, and that's what I'm going to show here. So we're going to use these formulas here. Here's the one that I used in the previous example, and this is geometric sum. But if we take this right here and rewrite it, the number of nodes at the level is 2 to the L power. So 2 to the 0 is 1. There's 1 node here. 2 to the first is 1. There's 2 nodes here. 2 squared is 4. There's 4 nodes here, and so forth. We have this right here. Multiply the 2 to the L power by each of these terms, which gives us this. We can separate out the summation, and that's where the formulas come into play, because this right here is the geometric sum. This is the other summation, which each has a closed form solution. I replace these by the closed form solution to get this for geometric sum and get this for the other one. Multiply those out. Here I'm using h as the floor of log of n. And if we replace the h by the floor of log of n, we have this. And just like before, we need to somehow do something with this right here. And we know it's bounded above by less than or equal of 2n, because this right here is less than or equal to 2 of n. And if we look at this, the dominant term is is big O of n. So it's this right here. That's the dominant term, which gives us a big O value of n as opposed to n log n. Technically, this right here is less than or equal to big O of n log n, so this is still true, but this is a tighter bound, which shows that the approach where we build the entire binary tree and then heapify it actually has a lower average cost, or in this case, worst case, a lower cost. So this is the approach we prefer in terms of sorting or just heapifying. So now it leads us to how do we use what we have here. So let's go back to this example where we started with 1, 2, 3, 4, and 5, and we solved to heapify. We end up with 5, 4, 3, 1, 2. 5, 4, 3, 1, 2. So this is the heap. And so what do we do now to sort using that? So for heap sort, so once again we build max heap, and we just saw this has a cost of big O of n, and then what we're going to do, so we swap the root and last element, which the last element here would be the 2. Okay, so that would be something like this. We would say now we have 2, 4, 3, 1, and I'm going to write the 5 here, because what we're thinking about is that we removed it from the array, or the heap, excuse me. Because what happens when we do this? In this case, we started with this. We had 5, 4, 3, 1, 2, and the entire thing is treated as a heap. When we swap these, we now think of this as being the heap, just those 4 elements, and the 5 is at the end of the array. It's still in the array, but we no longer consider it part of the heap. But what happens now? We have this. This is no longer a heap, so we have to heapify it. So now I heapify the new heap. And what does that consist of? Well, we swap 2 and 4. And why is that? Well, what we have to do is we look at this and figure out which of these is the largest. It happens to be 4. If the 4 had been over here and this is 3, these would be the ones that swap, but that's not the way it was. This is the 4. And now we have to compare 2 to 1, and had this been lower than this, like if this had also been 3 or something, we would move it down again. So this actually is now a heap. But what potentially could have happened here? We removed this node, the 5, by taking the last node and moving to the top, and potentially what could have happened is we move down to here, we move down to here. So an upper bound on the cost is that for a tree of height floor of log of n, to heapify, we have to move this many levels down, 1, 2, because this would be 2 in this case. So that means the cost of heapifying for each node is bounded by this, and we'll do this n minus 1 times. So this right here is big O a log of n, and so we do that n minus 1 times for this part right here, plus we have this right here. So this right here becomes n big O of n log n minus big O a log of n, and then we have the cost right here of this. So we add the 3, this plus this plus this. This is the dominant term of the overall thing. So the cost for heap sort, worst case, is big O n log n. So that's the answer in terms of the analysis of how it works. And as we showed here, this is why we choose this approach to do that. Okay, so this right here plus these right here. So what else do we know about heap sort? Well, a couple things. One, it's not stable. What does that mean? Well, let's say that we had these names. We had Smith, Ralph. If you see my other videos, you've seen the same example. We have Douglas, Charles, and we have Smith, Alex. Let's say we want to sort this by last name and then subsort by first name, which means that when we have a tie for last name, the first name should be in order, which means Alex should be above Ralph. One way to do that, if we had a stable sort, is we could sort by first name first, which would mean we would have, we would have Smith, Alex, Douglas, Charles, I'm just going to see, and Smith, Ralph. This would be sorting by first name. And now if we sorted by last name using a stable sort, because this came before this, it would remain above that. So the final result would be Douglas, Charles, Smith, Alex, Smith, Ralph. If the sort is not stable, it won't necessarily maintain that. So we still could get the correct order of the last names, but now we may have lost the order for the first names. So if you need a stable sort, don't use heap sort. But another property of heap sort that we can see here is it sorts in place. Now, of course, we're always using some temporary storage, or we almost always, let's put it that way. There's tricks around it in certain cases. But when we had our array, we simply swap things around using the same array. If we have something like merge sort, if you've seen my video on that, we know that when trying to sort merge sort, we may break this up into parts. So we'd have temporary storage where half of this goes over here and half of this over here, and now we copy these back. So we have to have additional large amounts of storage to do merge sort. So if you care about that, heap sort may be a better choice than this. But anyways, that's the analysis for the big O value for heap sort.